Hello, I am Barış Akgün. Today we will present our project, a guidance and tracking system built entirely in hardware on an FPGA. Tracking a moving object in real time is a critical capability. It is used in a wide range of areas, from missile guidance systems on UAVs to security cameras and factory quality control. The problem is that real-time video systems can run into bottlenecks when run on standard processors. A standard 640 to 480 image at 60 frames per second means processing 18 million pixels every second. The solution is to move the work into hardware. Instead of running instructions one at a time on a CPU, an FPGA let us build dedicated digital circuits that process the pixel stream in parallel in real time. Our platform is the TerraSeq DE1 SoC board, which contains an Altera Cyclone 5 FPGA. We wrote the entire system in System Verilog, verified it in simulation, and then programmed it onto the actual chip. What you'll see on the monitor in a moment is the result running live.
Hello, I am Şamil Emeç, and I will explain what the system does. On the screen, you will see that there is a white square moving and bouncing off the edges automatically. Similar to a classic ping-pong game, we can adjust its speed dynamically using the push buttons on the board. As an example, key 3 accelerates the target and key 2 slows it down, allowing us to test across multiple different speed levels. Now, if we focus on the red bounding box, we can see that our FPGA is calculating and drawing this entirely in hardware. This box indicates that our system has successfully identified and locked onto the target. As the white square moves, the hardware computes its exact coordinates every single frame and renders the tracking box in real time, without any noticeable latency. To test the robustness of our tracker, we also introduced two blue squares with their own randomized motion. These serve as distractor objects to test if the system loses the lock. However, as you can see, the red rectangle never jumps to the blue object, because our algorithm is designed to filter specifically for the white target. It completely ignores the distractor and maintains its stable continuous lock.
Hello, I am SAÐLAMER, and I'll explain how our system works. The design is a streaming pipeline. We never store a full image in memory. Instead, every pixel is processed the moment it appears, and then it's deleted. The system has 6 main modules working together in parallel. A VGA timing module generates the pixel coordinates as 640 by 480 pixels at 60 frames per second, exactly matching the standard VGA signal a monitor expects. The target generator moves the white square and tells the rest of the pipeline whether each pixel is part of the target. The tracker is one of the most critical parts of the guidance logic. As pixels flow past, it is looking for white ones and keeps track of the minimum and maximum X and Y coordinates. By the time the frame ends, it knows the exact bounding box of the target. The overlay module then uses that bounding box to draw the red rectangle around the target. At the same time, our FPGA also draws the blue distractors to ensure that the system simulates real-world visual noise.
Hello, I am Eren Özpolat, and I will discuss our final deployment, results, and conclusion. During development, we programmed the FPGA using a standard SRAM object file. However, this is a volatile memory, meaning that the design is erased the moment the board is powered off. For our final deployment, we wanted to ensure an FPGA independent from our computer. And to achieve this, we reconfigured the mode select switches on the board. And then, instead of using an SRAM object file, we generate a JTAG indirect configuration file and flashed it directly into the board's onboard EPCQ flash memory. Because of this change, our tracking system is now permanent and boots up and runs instantly whenever the board is powered on, with no additional computer required. In conclusion, our project successfully proves the extreme efficiency of hardware-level video processing. By relying on a streaming pipeline rather than a memory buffer, we achieved a continuous, almost zero latency lock on our target at a full 60 frames per second, while flawlessly filtering out visual distractors. This demonstrates that FPGAs are perfectly suited for high-speed, real-world guidance applications where CPUs run into bottlenecks. Thank you for your time and attention.